I'm Brandon. I was the founding engineer at O1 Labs, and we built Mina. And I moved around a lot in the org, and now I'm CEO. So because I'm CEO, I'm forgetting all these technical things. So forgive me if I'm rusty, but I did build a lot of this stuff. So we can go as deep as you want, whenever. So, but in this talk, we're going to imagine the ultimate ZK platform. Okay. So if you were imagining that, what could you want? You might want a platform that developers can build on easily, but powerful enough to really unlock the rich parts of the underlying ZK proof system. And you want everyone to be able to participate safely as an operator and as a user if you're building a decentralized system. You want devs to be able to build applications using privacy. That's a core part of ZK. If you don't have that, then you're not really getting access to it. But still interact with some kind of global shared state, even in a world where we don't trust everyone. And of course, being able to build on top of people with that shared state and scale. So, okay. Right. So, I mean, we can. I just said a bunch of sentences. We can break this down into things that are more small to say. So, easy composability. That means easy for devs, and it's composable under several different vectors, and we'll get into that. We want something that's private. We want decentralization of state, of the system itself, of the developers and the users, and when users are using it, all the way up and down. We want computational efficiency. We don't want to redo computation or pay too much for extra work. And this, my computer's too small. And yeah, I guess we want lots of people to be able to do lots of things. Cool. So how do we do it? Okay. Snarks, sharks, it's close together. So cool. So we want easy composability. And we still want to get power and juice out of the underlying proof system. So okay, the first thing is what is composability? Let's just get on the same page. I think of composability as being able to mix and match, and build really complex systems out of small kind of Lego-like building blocks. So if you have little Legos and you're building stuff up, in order to do really interesting things, you need some kind of recursive looping happening. If I combine 3 Legos together and I need to be able to plug that into a copy of the first Lego, right? And if we're talking about working with proofs and working with ZK, then we need proof recursion. So we need the ability to verify a proof inside of another proof. And it needs to be first class. Developers actually need to be able to use this thing in their applications, and it should be kind of unbounded. We should be able to build whatever Legos we want. Okay. So how do we make this easy? Well, okay, recursive proof sounds complicated. Recursion itself might be complicated for people, but the simplest form of recursion that developers have is functions. So if we model recursive proofs as recursive functions, then we kind of make it easier for devs. And we can put it in a language that people know and understand. JavaScript and TypeScript has the most developers in the world, so we can use that. And if we really have deep access to our proof system, then we should be able to mix in ZK VMs, classic Turing machine style ZK VMs. So being able to mix in Rust or Go or C code compiled down, and mix it in with circuit code, and then we can use recursion to kind of plug everything together. There's a trade-off with these things. When you use a ZK VM, things are usually slower. So it's nice to be able to kind of jump between them. So okay, that's sort of at the core level. But what about at the smart contract level and like with tokens, if we're thinking about a blockchain. Like contracts should be able to call other contracts. But like this is not so straightforward if you're modeling like smart contracts with privacy and with ZK. And you know, you can do something. You can do something interesting if you model like contract calls as a tree or like a forest of trees. Then you know, like, okay, if I'm in a function here and I call a function and that function calls a function and then that function returns and this calls another function, right? Okay. We can make this kind of forest and then reuse it to also model not just contract calls, but also like token permissioning. So you can have like a token contract here, and you can have an like someone who's using that token over here, and you can have, you know, a sub token here and a sub token here, and then a usage of this like double nested sub token. And you can reuse the same kind of tree structure, which is cool. We can go deep in that later if you're interested. So okay, easy composability via recursion or contract or token composition, and using JavaScript and you know, with the ability to mix in ZK VM compute and being able to plug it all together. Okay, privacy. So how do we get privacy in one of these platforms? Like, well, it means we have to create proofs client side. If we're not making proofs client side, then we're sending our private data to someone else, and then it's not private anymore. So we need to prove client side. Okay. But if we do that and we're in a system with shared state, then like how can we? You know, we sort of run up with these problems. Like if two people at close to the same time are kind of interact with the same state, then they collide with each other. You know. So there's races, and we need to be able to resolve these races. So one way to do that is you can use an action reducer system. So you can, instead of actually, you know, on each side saying like, okay, I make the state 3, I make the state 4. You say, I want to add 1 to the state. And over here you say, I want to add 1 to the state. And you can do those things at the same time. And then later, you know, one of these users or someone on in a backend or something can kind of combine all those things together. Then we don't have a race anymore. Okay, cool. So, decentralization. There's like a lot of different ways that we want to decentralize. We want retail hardware support because otherwise we're not going to have a decentralized network. So that means expensive work needs to be broken into enough little pieces so that different machines can handle them. We need, if we're thinking about a blockchain system, you know, if you think of a typical like ZKL2, you have to sequence, someone has to sequence transactions. But we need the sequencing to be decentralized if we want a decentralized system. So we need a blockchain with a consensus algorithm and all these things. If we're decentralizing the proving part, then, you know, we could farm proving out to a network and to a marketplace, and then like other nodes in the network can do these proofs, and they can bid on them and whatever, and it'll work. Okay, user interaction. If we want a real decentralized platform, users can't be using Infura and whatever. Like you know, really technical users are going to run their own blockchain node maybe. And you can configure in your dApps to like connect to your blockchain node, but that's not really decentralized for like the normal users, right? So we need a way where there's no middleware. If I just open a web browser and I'm trying to use an application, I can connect directly to a network in a decentralized way. And so I claim in order to do that, like we really need a single proof of everything all put together. Because if you have one proof, like that's small enough that you can send that around around the world and verify it quickly and all these things. So we need a proof of everything. And if we have a small proof of everything, then yeah, we can use it in the browser or on a phone or whatever. So So if we think about like what that means for our system, it means that everything has to be in a snark. That means the whole blockchain has to be in a snark, and all the consensus rules for the blockchain has to be in a snark. And every computation by every user on the network has to be folded into that snark. And this snark has to be constantly aggregated incrementally and consistently forever. And you know, this is, I think this is really cool. So like, you know, one interesting thing here, if you think about consensus, you know, this is like, how do I talk about this? Okay, so some consensus mechanisms require like, you know, rolling a fair like random die, and one way to do that is a verifiable random function. So it's this nice like cryptographic primitive that lets you basically do what I just said, or think of like throwing a dart at a dartboard where the dartboard is separated by like people's stakes in the network. So this is like one way to do a proof of stake consensus mechanism. Like these kinds of primitives, they use like weird functions like sine and cosine and like inverse square roots and things like that, and it's really hard to put those into a snark. And so like you might have to do crazy stuff like a Taylor series approximation. Isn't it cool that the AI like can make that? But yeah, so there's a lot of cool stuff that you can do. Okay, right. So decentralization, there's like a lot of vectors here, like people participating as operators. There's like the sequencing, proving that end users, when they're using it, can actually you know, do this in a decentralized way. And all of that put together means like we need a single snark. Okay, so computational efficiency. All right. Well, okay. If we have client-side compute, then like something cool happens just by default. Gas becomes predictable. So normally when you're using like a blockchain system, when you're interacting with a smart contract, you're paying, you know, per computational operation you're doing. And this is called gas. But if you're doing all the work client side, then on chain there's nothing to pay for. So that's cool. And actually, like, there's some applications where, you know, we have a backend service just because we need something to do computation in a trustworthy way, but we can just get rid of those if we have a way to do computation client side. Okay, so cool. Scaling. All right. Okay, so if we have our system as like one single proof, and we have recursion, we have proof recursion, and this is modeled with like recursive functions, and application developers can use that, then we can make. This is a very accurate picture. I'm just kidding. But okay, so we can make applications themselves just our mini ZK rollups. Every application is a ZK rollup because it's just a recursive function, so it's easy. Cool. Okay, so composability. We have composability through recursion easily, and client side using recursive functions in JavaScript through contract calls and tokens with like clever circuit reuse. We have in privacy, that means we need client-side compute. For decentralization, then we're decentralizing the participants, the sequencing, the proving, and the end user usage. And finally, well, two things: computationally efficient, as I said, and scaling through ZK rollups. Okay, cool. So this is Mina. You knew that, right? But yeah, so this is basically how Mina works. So Mina's been on mainnet for the last 3 years, but only with payments. So there was a single proof of everything for payments using, we call it a pickled proof system. So for people that know ZK proof system guts, it's like a Plonkish Halo 2-ish system that uses an inner product argument as its polynomial commitment scheme. We just learned about those earlier. And it's using the pasta curves. This is just like the name of the elliptic curve that the pair of elliptic curves that it uses. And it has decentralized sequencing. So this is using the Ouroboros consensus mechanism, and all of that is implemented in a snark. It has decentralized proving. There's this thing called the snarketplace on the system where like work is farmed out to different nodes in the network, and that work gets done, and the chain moves along. So coming soon is client-side compute. So client-side compute with what we call ZK apps that are composable off-chain through those call forests that I showed, and they use action reducer style, race reconciliation, and a bunch of other stuff. And a more powerful proof system. It's just kind of better, faster, and all those nice things. And we call it kimchi. It's still a Plankish Halo 2-ish IPA over pasta. And coming soon, not as quickly, maybe a few months later, but a full implementation of Mina that compiles to the browser and works on a phone, even a browser on a phone, so that when you're using an application, you can connect directly to the network. And it's programmable with TypeScript, and recursive functions are recursive proofs. And we've been iterating for a while, so I think it's pretty nice to use, and we still have a lot to do, and we're still going to keep working on it. There's also custom gates, which are a tool used to accelerate working with ZK proofs. And we have libraries like ECDSA and nullifiers and all these nice primitives that people want to use when they're building ZK applications. And even if you don't know any of those things, it's a really good place to start playing with ZK. And we have bridges coming soon. So what's cool is like, because Mina is a single proof, if you bridge it to another chain, it's akin to just like verifying the proof. And also it's sort of like makes Mina a validium for the counterparty chain. And there's a few different teams working on this, and a few different implementations. And it'll scale with rollups and rollup SDKs. And there's a couple that are coming along around mainnet time, Zecco and Protokit, they're called. So there's an upgrade scheduled for June 4th. You don't know how long I've been waiting to have a date. It's so nice that it's on the horizon. It's like 2 weeks away. So yeah, everything's basically ready. You have to have a date before exchanges are willing to start upgrading. So let's hope that they meet their deadlines. But yeah, the mainnet with all that stuff is coming soon. And then beyond, like we're working on a ZK VM for our proof system, but we haven't integrated it yet. It's high performance MIPS ZK VM, so it can run Go code or Rust or C, and more performance and more ZK app features and more bridges and more L2s and all that stuff. So yeah. So anyway, I work at O1 Labs, and we're hiring. We have a bunch of roles. Even if there's not a role here, reach out if you're interested. And yeah, that's it. Join the community, build ZK apps, contribute. Yeah, happy to go into whatever, questions, go deeper into stuff. We can talk later too if you don't want to say it in front of the crowd.
I have a question. So I saw that as a folding scheme, Mina uses Halo 2. Does it make sense to upgrade to Nova, or how so what performance gains would be because of it?
Are there markers? Oh, so yeah. So why not both? So there's, God, I always get this wrong. There's like this concept of like PCD, proof carrying data, right? So if you have, okay, let me take a step back. So there's like, I like to separate like proof recursion from folding. I mean, now there's some folding schemes that kind of give you a little bit of both, but bear with me. Okay, so like both of these things let you do a bunch of work and kind of aggregate them into a proof. And so, but proof recursion lets you like kind of incrementally at every step, you know, grow your proof. Where at each of these points, the actor in the network who's expanding the proof doesn't have to trust anyone else in the network. But when you're working with most folding schemes, it's much faster, but you have to trust all these people that you're working together to aggregate the thing on. And it doesn't work incrementally as well. So for something like the actual Mina blockchain itself, where every single block, we're kind of expanding the chain a little bit, the Halo 2 style proof recursion works really nicely. Folding is really good though for like certain applications and really good for the ZKVM. And so we are implementing it. It doesn't quite work yet, but yeah. So we're adding it to our proof system. Okay. I was long-winded, but.
So you mentioned that you want the ZK proofs, the ZK thing to work in the browser, and don't you consider it a privacy risk because like usually you want your cryptographic apps to be native to protect from this attack where the website that you're using changes the code that's run in the browser without your knowledge?
Yeah. Well, there's kind of a what is this called? Like I'll make up the term because I don't know what it's called. But there's what I'm going to call like a usability threshold, where it's unreasonable to ask users interacting with applications to download native code, sadly, for a lot of their, like, for normal people. Like, normal people just want to use the internet, you know what I mean? So I think like you're presenting a real issue. Like, it's important that you know what you're interacting with. But there's ways to get around that. Like, you can have your, this isn't implemented in the Mina ecosystem right now. But you know, like, probably you have like a wallet extension, let's say. So you have like, you know, if you have your application here, and you know, you're doing some stuff privately, whatever. You might have like some wallet extension that is running kind of more, it's like code that you trust. Like maybe there's some native code in it, or at least it's like you've installed it from some trustworthy place and it's static. You could have this system like verify that the code that's running here is kind of what's expected, like what's been registered. And like on chain, there's fields in the accounts where you upload smart contracts where you can kind of put like a SHA-256 hash of like a payload that you expect. So there's affordances in the system for this kind of thing to be built, but it's not built yet.
There's a simple solution. There is an add-in for Firefox, probably also for Chrome, which will check whether the website is properly signed with a GPG key. Yeah. But still, like most users, install the add-ins.
That's the problem, right? Yeah. But I think like the important thing, like ultimately, when you're using an application, like you need to trust that the application is like there's kind of like a root of trust thing. Like at some point you have to trust something. So I don't view this as like a huge problem, but it's nice that there's something that we could do.
I was wondering about the privacy bit.
Yeah.
You mentioned one way of overcoming the race condition was using the action reducer pattern.
Yeah.
It sounds like going against the DevX criterion, right? Like what can you
Yeah.
still do with this pattern, and how can you do even for payments only, like double spending prevention? Like, do you need UTXOs and nullifiers? How do you expand the realm?
So yeah, there is like a DevX hit that you take when you're working with actions and reducers versus just like being able to execute code sequentially. And actually, there's a ZKL2 in the Mina ecosystem called ProtoKit that has just decided like, hey, it's too annoying to have to put everything in this action reducer pattern. Like, I'm going to have a system that has on-chain execution, but in exchange, like that on-chain execution portion doesn't have privacy. But I will argue that the DevX isn't that bad because this is like a common pattern in like UI development on the web. So working with state in React uses this kind of action reducer pattern, and it's
well, no, like
no?
You can just set state to something constant.
Mm-hmm. Yeah, but when you have a part of your state that is where there's like concurrent, there's like different button presses that are updating state and all this stuff. You use the whatever it's called now. You use reducer, right?
Until a few years ago, there was Redux. I think that was
Yeah.
the default way of doing it, but they abandoned it a few years ago.
But there's still use reducer, right? Like
yeah, but you can set things explicitly. I guess that's the difference.
Yeah.
I wonder, is this even Turing complete? Like, can you actually express everything in the action reduce pattern? Like, how do you achieve synchronicity? How do you check whether the guy, like the counter is 17? Can you do it?
So this, like, you only need to reach for action reducers for the parts of your application where there's going to be a lot of concurrent stampeding, right? Like, nothing's stopping you from just writing code that's going to have races. And in that world, it's like just one person wins. And actually, in using like actions and reducers, you can have an action of like, hey, I want to overwrite the state to whatever as your action. And then the reducer can specify what conflict resolution mechanism you want to use, which is cool. So you can always do that. And yeah, like the reducer, so there's, I'm going like deep in the weeds here, but we have the system set up so that like you can reduce partially, and that way it prevents races on the reduction, which is cool. So like the blockchain's aware of a few of the most recent states. So if two people are reducing at the same time, the system will still kind of get up to speed. But yeah. Anyway, it's really cool. I'm into it. But yeah,
He's an engineer.
I'm an engineer, as you can tell. No. Yes. So. Yeah, it's not perfect. But if you want privacy, then like you need to be doing computation client side. And so I think like ultimately it just comes down to designing your application in the right way so that the things where there's lots of concurrent writes happening, you need to push that to action reducers, or else your users are gonna have a bad time. But for the parts of the application that don't have that, you can write code more traditionally.
So how is double spending avoided?
So I should make this more clear in my presentation. So Mina at the base layer is transparent, and there's an account model. But you can build a UTXO model on L2, and actually there's someone in the Mina community is building that.
So the payments are not anonymous right now?
No, but you can build an application with anonymous payments at the L2 layer. Yeah, and that's intentional. There's, in the United States, doing things with, when your base layer is private, sometimes the government doesn't like it. So we like the government video recording, and it's as long as the base layer is transparent, giving people the tools to use privacy is, we think, enough.
A question from my side, because you also says that the blockchain is 22 kilobytes. And how do you deal with the state load? Why?
Yeah. So.
I think the projector is off.
Oh, okay. Then I won't pull it up. It's okay. It's okay. It's not important. Yes. So. So the 22 kilobytes, there's a blog post on the homepage. If you click on 22 kilobytes or something, it explains. I wrote it like a bunch of years ago, so it explains all the details. But luckily, I'm here, so I can just tell you what's in it. So the 22 kilobytes is the amount of state that you need to connect as a full node without trusting anyone and verify that your account is up to date and part of the network and whatnot. Okay. The state of the system, so like full nodes on the network, like with full node security, only need that 22 kilobytes. But nodes on the network who are processing blocks, who are actually creating blocks, block producers, that's what we call them. Block producers need to have the states, the current account state of all the accounts that they want to be able to process transactions for, right? But it's still, even in that world, it's still nice because on Mina, as the system goes along, like most blockchain systems, they're kind of like O of transactions. But Mina, well, like full node secure, but like unable to produce blocks, those are O of 1, O1 labs, get it? But for the block producing nodes, it's O of the number of accounts. So it's linear in the number of accounts. This is the state that you need to keep. Yeah.
That's pretty good.
Yeah. So it's cool. It's still much like this is so much bigger than that over time. So yeah.
And the O of 1 is possible because of ZK. That's why I don't need to check the counterparty.
Yeah. So
I just want to run the super lightweight thing.
Yeah, so specifically, yeah, like there's, so Mina, like if you say like, okay, what is the current Mina blockchain like state right now? Like what does it look like? It's a snark proof, pi, I guess, and then snark proofs have like public witnesses that you have to like pass in when you're kind of checking if the proof is valid, and the public input to the proof is something that's like, the Merkle root of the ledger with like all the accounts is A, B, C, 1, 2, 3, whatever. It's like some hash, but it's not a SHA hash. It's a hash in our yeah, but whatever. Okay. So it has the Merkle root. It has the block height, the block hash, the kind of normal stuff that you'd expect at the tip of a blockchain. And this is 1 kilobyte. Like this is 5 or something, and then like the metadata that you need about your account is the other 15 or so, and that's how you get to 22. So.
And to create the ZKP, do you actually use this WASM TypeScript thing, or are you able to somehow prove an interpreted language, like the real TypeScript?
Right. It's it is TypeScript. It's a framework in TypeScript, kind of similar to React in that it's like you're using TypeScript. You have if statements and things, but like when you're working with the circuit components, the actual like ZK proof that you're describing, you're manipulating like WASM black boxes and plugging them together. Otherwise, it would be way too.
So no JavaScript, only TypeScript.
JavaScript will work too. Yeah, it's just like easier in TypeScript. TypeScript, you can like erase the types, and it's JavaScript, interactable with JavaScript. Yeah, but yeah, the actual at the runtime level, it's like using some building blocks, but the building blocks are made in such a way. We came up with this when we were making Mina. But like, okay, when you're working with like low-level zero-knowledge proof circuits, they're called, or like when you're working on provable programs, you're trying to describe a program. At the actual implementation layer, it differs a little bit depending on your proof system, but ultimately, like you're manipulating. You're kind of like manipulating constraints on field elements, the like a primitive in the at the kind of lowest level of the proof system. So like if you want to do something with a list of booleans, right? Like it's kind of like you're writing assembly, like metaphorically, where you have to think in your head like, okay, how does this map to my low level primitives? Like and it makes you go crazy. So when we were making Mina, we had to do so much in snarks that like it was impossible to like think at this low level. So we built this this kind of abstraction layer where if you provide a bijection, right? Like so you can say like, okay. What's a good example? Like, let's say I want to do like if like my Boolean is true, then then X else Y, right? I have this kind of like expression that I want to represent, right? I want to think about it as like if B then X else Y, but in like the lowest level parts of the proof system, we write this like b times, what is it? B times x plus like 1 minus b times y. Did I get that right? Right, because it's like 1 times x and then 1 minus 1. If true is 1, right? True is 1 and like false is 0, then this expression evaluates to x if b is 1, because this goes to 0, and if b is 0, then this goes to 0, and this is 1, and so we get y, right? So if I provide a bijection between some representation of this of this version of thinking about things to this version of thinking about things, then I can write software that looks good, and I get this behind the scenes, and I don't have to think about it. This is maybe this wasn't helpful. It's a very high level, but yeah, like and this, you can do this to build like complex data types, right? At the kind of assembly level, everything's a field element, kind of like on a computer, like everything's an integer at the lowest level, but I don't want this to be ever not 0 or 1, and so I can build like an abstraction layer on top that prevents it from being 0 or 1, but it like bijects down to representation in the field world. And you can build complex structs and big collections and all these things, and then you can build a Taylor series approximation of a verifiable random function that you put in a consensus mechanism, et cetera. So we took this system and we ported it to TypeScript, and so it's available for developers, and then we built like tons of these nice abstractions. So you can do like, you can work with, all kinds of useful data structures, and you have the tools to like make them yourself.
Well, this is true for C, but how you can't have a bijection in an interpreted language, right? You would need to have your VM, like JavaScript VM. So I assume you must be transpiling or transcribing the JavaScript to something compilable.
Yeah. Think about.
This explanation is very, very good.
I mean, this works for C, right? You can have a bijection, but I wonder how to do with an interpreted.
All right. I'm gonna pull up. I'll show you. It's not so. Think about like at runtime in the browser. There's like two phases. There's a phase where we're executing the JavaScript or TypeScript, and it's assembling. It's like compiling essentially, like to build this black box of all this WASM that describes the actual program, and then the second phase is feed that black box to the proof system, and you get a proof. Does that make sense? Maybe I didn't need to put my computer. So what that means is like, I wanted to show an example. Well, I'm not connected to the internet, so it's fine. Anyway, look at go here, go to docs, look at CCAPS, TypeScript, how to get started, and there'll be some examples and it'll make sense, I think. Okay, cool. Any other questions about Mina or building applications?
More kind of.
Yeah.
So I can understand how you verify, like single user verified something, but how it's going to be with scale? Like
Good question.
it's like some kind of sequencer to validating for the user, or usually validating then with another validator.
If it's wet, I can't use chalk again. This is a flaw in the system. Okay, I'll just, yeah, okay, so how does it, I think this is really cool. So I'm excited that you asked that. Maybe I can, whatever. Okay, so here's the browser. So a proof, like the user on their laptop or something, or their phone, creates a proof pi of their like interaction with an application. Okay, so then what we do is we take this pi and we stick it inside of a transaction, which I'll draw as a triangle, and then we send the transaction to the blockchain. So that the transaction has the pi in it. It also has like, this is my account, this is my public key and a signature and all these things. And then the transaction goes through the blockchain network, and it eventually gets queued to create a snark for the transaction by nodes on the network. But all the privacy stuff is already done. So now another node on the Mina network, it's called a snark worker. A snark worker will take this transaction that has a proof in it and make another proof, pi squared. Okay, and then these pi squareds are assembled in a tree. I'll do 4. And then these are combined into new proofs. I'll call it pi cubed. And what this proof says is like the transactions. So this what this proof says is the transaction applied to ledger state A was successful, and it created ledger state B. And this says B goes to C, and this says C goes to D, and this says D goes to E. So what pi squared says is that a single transaction is valid, and as part of that, this pi is valid. And then pi cubed says if I have 2 pi squareds that are valid, that go from A to B and B to C, then I have one that goes from A to C. And then we do this in a tree until we get to a single one. And then this single proof that goes from A to E, but the tree is much bigger, this gets folded into another pi to the 4, which is the blockchain proof, which is the thing I drew earlier that expands by 1 every block. So only at the lowest level is this happening on a device. These are all done by different nodes in the network. And there's just like recursion all the way down. And even this pi can be a ZK rollup, which means it has its own recursive pies. And those pies can be in trees, and you can do crazy shit. Yeah. It's cool.
So it's like ZK apps will scale on that level that you don't like. I don't know.
Yeah. So ZK apps, like if you're building a little roll up in your application, then you're probably going to offload that to a service to do the rolling apart. But you could also do that on the client side. Yeah. But the actual like interaction of the application, it goes through this path before it gets into the blockchain. Maybe that was not the question you asked, but you gave me an excuse to talk. So.
Okay, cool. So like each part is like one node or no, like
yeah, so this is one kind of node that does this part, and then a different node does this block. Yeah.
What about preconditions?
Mm-hmm.
Transactions preconditions, because like what if the first transaction changes a piece of state, the third one depends?
Yes. Good question. Yes, there's a mechanism for dealing with that. I don't have any room to talk about it. Well, I'll just have to talk without a whiteboard. Yeah, exactly. If your application is like, hey, I want what's a good example? A counter. Yeah. So that you would if you were reading. So we talked about writing uses actions and reducers. For reading, so this isn't fully implemented yet, but it's close. But the way to solve that is and for some parts of the system, this is in place, but you have a way to say like, at this block, it was this value, or you can say like, give me this value, and like I don't care if it's 10 blocks old or 5 blocks old or something, or you care, and it's like only I want the latest one, and if it changed out from under me, make my proof fail. But yeah, it is harder to work with like reading state if the state can change out from under you. And you know the ways around that. Are using preconditions that are inequalities, right? Like the counter is greater than 3, and your counter is increasing. But yeah, it's one of those things like with privacy, it gets harder.
Right now, like how, because it works, just not so efficient, right?
So how the
So basically, like the transaction will fail if a precondition fails.
yeah, exactly. And the precondition right now is on the entire state of the account or the state of the ledger.
Yeah, like you have the ability to do either. Yeah. So I guess the way to think about it is it's on the state of the blockchain, but the state of the blockchain has a handle to the current ledger, and the current ledger has the ability to look at the accounts in the ledger, and so you can look and see, hey, this particular account that's in the ledger in the current state of the blockchain has this state. Yeah, that's how it works.
So how is private shared state possible?
Private shared state, private and shared are
yeah, right. So how can I
are not the same. Well,
count that it's
yeah, there are ways though.
I mean, private and shared. Well, MPC, FH.
Yeah.
You have it, right?
Yeah. So and there's less fancy things, like you can have there's like the Diffie-Hellman key exchange lets two people have two.
Can you do it?
Yeah. Actually, there's we have an implementation of RSA, which is in our standard library now, or if it's not in the, well, if it's not yet, it'll be announced soon. Yeah.
It is something like playing poker. Have like a state that pertains to everyone, but not everyone knows it.
Yes. Actually, there's a cool poker. Do we have a write-up of this somewhere? Well, in poker, like your hand is private, but you want to make sure that that you pulled your hand from a shuffled deck, and you want to make sure that one person pulls their hand, and then those cards are not in the deck anymore, but the deck was shuffled fairly, and the remaining cards are still random, but the ones that are in your hand are missing, but no one can know what those are, right? This is like the problem. There's a fun thing you can do with groups, and you can play with the property that you were showing us with Peterson commitments, where this is an exercise for the reader to figure it out. But you can do fun stuff with groups because of the homomorphism of multiplication. And this lets you make a shuffled deck and cards and stuff. I can pull up. I don't remember the details. I can pull it up and remember it, but it's cool.
Yeah, if you wanna Google it, it's called mental poker. The algorithm.
No, we have a different implementation. Now you make me curious. You know what? I'm pulling it up. What? I don't have Wi-Fi.
When we get to Wi-Fi, how about we wrap up the live stream?
Yeah.
I bring in the pizza and we continue.
Yeah.
With